Parallel plate force problems, lesson 7. Shush, please. Quick review from last lesson. We said, if you got a couple of parallel plates, charge one positive, charge one negative by hooking them up to some kind of an electric source or a battery. The electric field is given by the change in voltage divided by the distance between the plates. By the way, you may notice in your formula sheet, if it's an equation that you can use for point charges, we use the letter R for radius. So this is a, let's go that. This is a point charge equation. This is a point charge equation. This is a point charge equation because they have R's in them. And by point charge, what I mean is planetary charge and small electron or proton or something like that. If it's a plate equation, it's got a D for distance. If it's a definition, which means it works for both, it doesn't have an R or a D. These two are definitions. We defined electric field as force divided by charge. We defined voltage as how much energy per coulomb. So those two there are universal and can be used in any situation. You adapt them. If I want to find this and the voltage between point charges is that, then I can say KQ over R equals change of potential over Q. Or if I want to use this and I get the voltage by itself, E times D equals EP over Q. There's all sorts of different variations that pop out of here. So back to here. We know this. Also, I defined, if you'll recall, our second definition of electric field was force divided by charge. That was how we defined it. What that means is I can rewrite this. I can rewrite this as the amount of force, electrical force, on a charge is equal to the size of that charge times the electric field that that charge is in. You want to know how much force a particular charge, like an electron or a proton or some kind of made-up charge in millicoulombs is experiencing? You tell me how big the electric field is and how big that charge is. I can tell how big the force is that it's feeling. Big deal. Actually, huge deal. This is going to explain, among other things, lightning, which is what we're going to be talking about for the next while. Example 1 says, explain why an atom will be ionized. The electron will be separated from the atom. So in science 10 and in chemistry, you learn ions are elements or atoms that are not neutrally charged because they have either gained or lost electrons. Emily, we're specifically going to be talking about losing electrons, ripping off electrons, as a matter of fact. We call that ionization. So I wrote here, explain why an atom will be ionized if you place it in a sufficiently large electric field. Well, inside an atom, this negative electron is attracted to that positive nucleus. You have the force of attraction. However, if I apply a big electric field, what direction is the electric field according to that arrow, to the left or to the right? To the right. Which way will an electron want to move then? Careful, think about it. To the left. This electron is going to experience a force that way. We'll call that the electric field force. And if the electric field force is bigger than the force of attraction to the proton, it's going to get ripped off of the atom. You have ionized an electron. Would it be easier to ionize valence shells or electrons that are in close? Oh, the closer you are, the stronger the force. The further you are from the nucleus, the weaker the force. So the atoms that are further out on higher shells are easier to ionize. The electrons, I said atoms. The electrons that are easier, that are further out from the center, from the nucleus, easier to ionize. Now, specifically what we want to look at today, Zach, is air, which is mostly nitrogen and oxygen. Yes, there's other stuff, but mostly nitrogen and oxygen. Turns out you can ionize electrons from air with about 3 million volts per meter. If you have an electric field of 3 million volts per meter, you can separate electrons from nitrogen and oxygen air molecules. Great, and that may sound like a lot, but actually it happens all the time. It is the crackle that we hear when we pull apart clothing that come out of the clothes dryer. That's ionization occurring. It's the shock that we get when we walk across a carpet on a cold winter day and then reach for a doorknob. That's ionization occurring. Oh, and it's lightning. That's ionization occurring. Ionization of the air, of the atmosphere. Dylan, each of these effects are accompanied by a spark or light. And the reason is when the electrons are ionized, they are free for a split second, but then very quickly they fall into the orbit around a neighboring atom. And when they do that, they lose some energy. The energy's got to go somewhere. Photon of light. So it's a conservation of energy effect. You don't need to worry about that, but kids always ask. Big deal. Actually, here's what this means. We can treat a cloud as though it's a parallel plate. Because relative to the Earth, I mean, I know the Earth is curved and bumpy, but over a big enough distance, it's close to being flat. And a cloud, although it's bumpy, although, you know what, over a big enough distance, it's close to being flat. So, Courtney, for the sake of simple math, we're going to treat the cloud and the Earth as two parallel plates. Example 2. The bottom of a cloud is charged to 2.5 times 10 to the 8th volts. How does a cloud get charged? We think right now by cosmic rays. And that's only about 5 years or so that we've thought that pass through the atmosphere. How close does the cloud need to be to the ground for a lightning bolt to occur if the air breaks down at about 3 million volts per meter? Well, we have parallel plates. I see volts and I see volts per meter. I think what they're talking about is the electric field, which we said last day was the change in voltage divided by how far apart the clouds are, so how far apart the plates are. What's this question asking me to find? Distance. Let's get that by itself. I think the D moves up and the E moves down. I think the distance is going to be the voltage divided by the electric field. How many volts has this cloud been charged to by the cosmic rays? 2.5 times 10 to the 8th. How big an electric field do we need before ionization can occur, before we can start passing electrons along the air molecules, therefore creating a current to the ground, a lightning strike? 3 million? How close does this cloud need to be to the ground Now, by the way, in this example, the cloud is positively charged, the ground is negatively charged. What moves when we're talking about electricity, protons or electrons? Shoshan, this would be a ground to cloud strike, not a cloud to ground strike. Still be deadly, still be yucky, you don't want to be part of it, but, and you wouldn't be able to really tell because it moves at the speed of light, basically, but 83.3 meters. There's several types of lightning. There's ground to cloud, like this. Cloud to ground would be if the cloud got charged negatively compared to the ground, because the ground is actually neutral, but if the cloud is positive, now the ground is negative compared to it. If the ground is negative and if the cloud is negative and the ground is neutral, now the cloud is positive compared to it. So that's when it goes from cloud to ground. You can also jump from top of cloud to bottom of cloud if two clouds have different charges separating between them in between them, or from cloud to cloud if two clouds have different charges. So example 3, you may know this, but now you know why. Where would you not want to be in a lightning storm? Brett. Okay, first of all, this would be bad because it's reduced the distance required for ionization to occur. Yes? So you might be safe right here, except the lightning's not going to hit you. It's going to hit the tree because the tree is way closer, and that tree's got to conduct that electricity somewhere. Some of it's going to hit you. That's why you don't take shelter underneath a tree during a lightning storm. Here is bad as well. Hikers in the mountains get hit all the time, not because somehow they're more conductive. They've reduced this distance up here. They're higher. Now, in a boat, there are two situations. If you have this kind of a boat, that's not good because almost all masts are made of aluminum. They're basically lightning rods. We don't deal with lightning too much here on the west coast. Out on the east coast, especially in the U.S. South, in the Florida area, lightning is a real issue because lightning storms on hot, humid days can go from a blue sky to a lightning storm in about half an hour. And so sailors out there keep an eye on the weather all the time, and if they see the barometer changing and they see any hint of a cloud on the horizon, you fire up your engine and you start making a beeline for shore as fast as you can because you're basically sitting in a lightning rod. Not good. Anybody been on a lightning storm out in the prairies? Far more intense than we get here. Yes? Yeah, we really don't get anything compared to what they get out east or on the prairies. Why on the prairies is it so much more intense? Well, there, all you have to lower the distance is trees, which means you have to build up a huge voltage and a huge electric field before the first lightning strike can go. Well, now it's on. I mean, the nice thing is trees and mountains kind of act like safety valves or release valves for some of those charges that are built up. And so we really don't get these huge, huge, huge thunderstorms that they get out east. Also the issue with water, let's be consistent in my coloring system, Mr. Duke. Also the issue with water is even if lightning hits right there, water is so conductive that it will transmit a fair bit of the charge to you. That's not good either. So Brett is right. It really in none of these locations. Where is a nice, safe place to be? Why inside a car? No, it's nothing to do with the tires. The lightning has just jumped 100 meters from the sky. I guarantee you it can travel 1 foot further and get to the ground in spite of those tires. I guarantee it. That's, by the way, every year a kid says that first thing because it's a very, very common misconception. It's nothing to do with the tires.
Is it the same?
Go ahead.
Is it the same as that video? Like if you're in like a metal cage?
It's a Faraday cage, yeah. A car is a Faraday cage. Like charges what? Repel. So if you're inside a metal object, even with windows and stuff, if you're inside a metal object and it gets hit by lightning, those charges want to repel each other. Tremendously they want to repel each other. Where will they gather? For them to get as far away as they can from each other, they're going to gather on the outside of the metal frame as far away as they can from each other. You might fry some of your instrumentation. You might fry some of your electronics. In fact, you probably might even feel some of the hairs on your arms standing up, and you may even get a shock. But nothing close to terminal. Nothing close to terminal. If you are in a lightning storm, and it's a nasty one, pull over, wait for it to dissipate, sit in your car. Oh, how long? Well, if my car got hit, I would stay in for a while because apparently I'm at the right condition for this strike to occur. The distance and the voltage and the electric field apparently are in the magic butter zone. I'd probably stay there for 10 or 15 minutes and then I'd happily get out, but you're good. So, lightning. Recall that if we know the field, we can also find the electric force on a particle as follows. Remember earlier, Sam, I said this. Electric field was defined as how much force per charge. I guess that means that I can also think about electric force as how big the charge is at that location times how big the electric field is at that location. That's not on your formula sheet. This top one is. I'm going to, Sam, I feel it's fair game to expect you to clue in that you can rearrange that. Oh, and we have, why did I spell also backwards? Good gosh, that's the second time I've done that now. There's a Freudian slip, right? You write one thing, you mean another? I don't know. Also, we have a couple of definitions for electric field now. Show between point charges, electric field is K big Q over R squared. That's if you know the size of the planetary charge that's sending out its octopus-like invisible electric field in all directions. Or electric field is the voltage divided by, technically the change in voltage, divided by the distance between the plates. That's if you have parallel plates, which means, Rob, I can plug each of those in for the electric field portion of that force equation and get new stuff. Oh, and remember, Graydon, we said this. R, that's point charge at radius, D distance, distance between two plates. Example 4. Now we can start to direct and move and control charges. We're starting, Jimmy, to get to the whole notion of, we're not there yet, but we're starting to get to the whole notion of a particle accelerator. Some of the physics that goes on in them. Find the acceleration of a proton, sorry, of an electron, Mr. Duke, placed in between metal plates that are separated by 2.5 centimeters in charge at 275 volts. First of all, look at the picture. Which way does that electron want to move? I heard down, I heard up. Convince me. Up. Why? It wants to go towards what? Positive and away from? Okay, it really wants to move up. There's my net force. What's this question asking me to find? Oh. Acceleration, well, force equals mass times acceleration. Which force is pushing it up? Electric force is mass times acceleration. Now, we have several expressions for electric force. I have K, Q1, Q2 over R squared. Do you see a planetary size charge and a secondary charge and a radius? No, I'm not using that one. You know what? I'll use my definition of force that comes out of my definition of electric field. I'm going to say Q times the electric field equals MA. They didn't tell me the electric field. I need the electric field between two plates. Q, change in voltage divided by distance equals MA. Right? What'd they ask me to find? Oh, get the A by itself. How? Divide by, oh, this actually turns out not to be too bad mathematically. We're going to get the acceleration is equal to QV divided by MD. All right. Q. It's an electron. Oh, I hear somebody turning a page, looking. Thank you for not disappointing me. The rest of you, please. 1.6 times 10 to the negative 19. V. How many volts is this electron traveling through? 275. Good question. Ask. Okay. I did say that for forces and fields, forget the sign. This is not a force. Well, this is sort of a forces question. Technically, the charge is negative, But because the electric field is defined as being from positive to negative, and we are traveling from negative to positive, technically we're also traveling in a negative displacement direction. Technically the D should be, you know what? The answer to your question is, if you ignore it, we're just fine because we want a positive acceleration. Really, that's my explanation to you is, I know ahead of time I do want a positive acceleration, so just leave everything positive. Okay? But there are mathematical reasons why we have, but they're complicated. Mass. It's an electron.
9.11 times 10 to the negative 31.
You have that memorized? You have that memorized? Or, oh, you looked? I have the 9/11 part memorized, but I can never remember the rest of it. Distance. Oh, don't say 2.5. Yeah, 0.025, because it's centimeters, right? Crunch the numbers and get a staggering acceleration. Make sure you put the bottom in brackets because there's more than one number down there. Kemi, what'd you get? Oh, still punching it in?
1.93.
You got 1.93? Units, it's acceleration. Mr. Dewick? Yeah, Chase. I got a problem with that. What's your problem, Chase? Well, Mr. Dewick, I've learned enough nerdy physics to know that the speed of light is the fastest anything can travel in the universe. And I know that the speed of light is 3 times 10 to the 8th, not 10 to the 15th, 10 to the 8th. That means if this electron is traveling for 1 second, it's going to be going almost, starting at rest, it'll be going almost twice as fast as the speed of light because it'll hit 1.93 times 10 to the 15th meters per second in 1 second. Isn't that violating like that whole light cosmic speed limit thing? If it was traveling for a total of 1 second, sure. But how far is it traveling, Chase? How far exactly is it traveling? 2.5 centimeters. You can actually crunch the numbers if you want to work out how long that's going to take. It's like traveling for like a billionth of a second. It's not going to get, even though it's going through a tremendous acceleration, it's going to hit the far side, and now it's gone through the entire electric field. There is no more extra energy to boost it on its way. It's maxed out at speed. We're not violating, but every year I have some kid who raises that. Actually, every year I do the same little speech and try and point out to you that you should be a little nervous about that number, but it's okay. We're not traveling for a whole second. What's the charge on an electron? More specific. 1.6 times 10 to the negative. What's the charge on a proton? 1.6 times 10 to the negative 19. The elementary charge, it's positive or negative, but it's that charge. How the heck did they find that? Because that's pretty small. Well, in a very famous experiment to measure the charge on the electron, Milliken used parallel metal plates to hold in place a charged oil drop. The oil drop remained in place because the electric force, due to the metal plates, balanced the gravitational force. See, the problem, Sam, if you want to try finding the charge on a single electron, its mass is so small, gravity won't really be there. So what Milliken did is he got an oil droplet which had enough mass that gravity did want to pull it down, and he suspended it between two plates. In fact, in terms of a free body diagram, we would say this. What are the forces acting on this drop? Get the obvious one. But it's not falling because electric force up was the same size. And we can completely control that electric force by simply dialing the voltage up or down. We would keep the distance constant, but we could dial that voltage up or down, and we could eventually move that oil droplet up or down, get it in a butter zone, and we suspend it. Part A says, what's the sign of the charge on this oil droplet? Positive or negative? Look at the picture and figure it out. This oil droplet. Sebastian. Oh, sorry? Positive? What's the top of the plates, positive or negative, in this diagram? What's the bottom of the plates? So if it was positive, which way would this droplet really want to travel? Down. We want our electric force to be up. You know what? The charge on this droplet must be... By the way, if it was positive, in other words, Sebastian, if we were doing the experiment and we noticed it went straight down, flip the wires on your voltage and just charge the bottom as positive and the top as negative, and you're good to go. So it was a fairly easy fix as well. B says, write a balanced equation. Well, gravity equals electric. But we can do more than that. mg equals q times electric field. But we can do more than that. Gravity equals q. What's electric field between parallel plates? And so what Milliken did was he was able to measure the mass of these oil droplets very accurately. He knew G. He measured the distance between the plates very accurately. In fact, when he set up the experiment, he just decided, I'm going to use the same distance over and over. I'm willing to bet if he was really clever, he would use 1 centimeter, because it's a 1. Nice math. And he had, even back then, we could control voltage very accurately through analog dials. Solve for Q. 1.6 times 10 to the negative 19. It's actually a tiny bit more complicated than that. I'll show you a video on that in just a little bit. But let's look at an example. Example 6. A particle of mass 2.3 times 10 to the negative 14 kilograms with a charge of negative 3 electrons, or elementary charges, is held suspended between the parallel plates. What is the voltage on the upper plate in order to keep the charge in equilibrium? Say what? Well, if it's suspended, Graydon, I think what we're really saying is gravity equals electric force. They're canceling each other out in opposite directions, but I don't care about the direction right now. mg equals q, change in voltage divided, it's QE, but E is the change in voltage divided by the distance. What are they asking me to find in this question? Oh, get the V by itself. That's going to be m times g times the distance divided by the charge, I think. Mass, I think they gave it to me. Yeah, there it is. 2.3 times 10 to the negative 14. You okay there? Mr. Marshall, you're right there? Okay. 0.015, 1.5 centimeters, divided by, the charge is 3 electrons. Again, I'm going to ignore the negative because I want a positive voltage. I can look at the diagram. 3 times 1.6 times 10 to the negative 19. 3 electrons. How many volts would you need for this system? Now again, Milliken wasn't interested in the voltage. He was interested, Jimmy, in finding Q, so he would change the voltage until he got it hovered. We'll show you a video on that in just a second. So about 7,040 volts, if I go to 3 sig figs. Yep. Yep. So parallel plate force problems. Emily, what we've added is we've said, look, we have two definitions of force now. Force between point charges, K, Q1, Q2 over R squared. But the universal definition of force is, well, if electric field is force divided by charge, then charge times electric field, that'll be the force no matter what situation we're talking about. What's your homework? Here's what I assigned my block A's. I gave them 1, 2, 3. I said skip 5, skip 7. So 1 through 10, skip 5 and 7. 1 through 10, skip 5 and 7. One, 2, 3, 4, skip 5, 6, skip 7, 8, 9, 10. A couple videos to show you, and then I'll turn you loose.